Okay, so this leads to the idea of impulse response leads to the idea of convolution. So if we take a look at that representation of input and output of the system, and now we have found how to find the output for any input. So as long as we know the impulse response, we can find the output to any input. But that idea of the impulse response is not just restricted to LTI systems. So if you just pull back from the practical and just look at the math for a second, we could really have any functions underneath that integral, not just something that represents an input and something that represents an impulse response. It could just be any two functions. Let's just call them f and g. And this construct is extremely important across all sorts of different fields. And because it is given the name, and it's actually got a mathematical operator associated with it, like multiplication, like division, like take the sign of an input. And so we actually have a mathematical shorthand for it. So this integral, which by example we see for systems and impulse responses, but that integral form actually has this mathematical shorthand, and it's called the convolution integral. Okay? And this asterisk here in the middle of those two functions, it's just a symbol, just like x for multiplication, just like slash for division, just like that cross for the plus sign. It's just another symbol, but it means take the convolution of f and g. So it's a mathematical shorthand for do this integral. And if you think back to our system perspective, we can actually reconstruct the input as a convolution of x with an impulse function. We'll see why in a second. And then the output is represented as the convolution of x with the impulse function. But what you actually have to do is solve this integral. Okay. So we're most interested in for this course anyway, we're most interested in the utilization of convolution for finding the response of a system to a given input. The procedure for calculation of that is, as I've told you, not very fun. It's actually mathematically tedious. However, doing these things by hand and seeing it visually helps to give a better appreciation for the underlying idea of LTI systems. So that's why we are going to do a few examples of calculating convolution by hand, and you're going to get a few more examples to try yourself. And in the future, this is sort of the carrot that's held out in front of you, we're going to learn some other techniques to be able to get around convolution. But first you have to experience why it's so painful, unfortunately. Okay, so we're going to do an example of the convolution integral, but first I want to give you an appreciation of what's actually going on when we're calculating this thing. And I've just used tau here instead of lambda. It doesn't really matter. We're going to take a look at a GUI here in a second, a MATLAB GUI, which is going to explain things. But if you take a look at the integral of interest for doing the convolution, you notice that we're integrating over tau. So the first thing we want to do is think of x and h as functions of tau. And note that x is not changed from its functional form, but h actually is. It's actually flipped, so it's time reversed and shifted. So in this example, if this was x and this was h, you notice that we've done a time reversal, so we've flipped h compared to here, and then it's going to be moving. So for each value of t, we're going to be calculating a value for y of t. And what's happening is when t is fixed, these functions overlap, but they're multiplied together And so all we have for these particular functions, all we have is this area here. And the reason I'm indicating it as an area is because we're going to integrate it. So it's the total of this area that is actually the value of y at that particular value of t. Okay? So we have to imagine that this flipped signal is overlapped with x. We multiply them together to get this function. We're integrating it. That gives us some value, and that is the value that we of y at that value of t. Okay. So first, we're going to get some function for x, and let's just use a step function. And then we'll use that same exponential for h. So that's our impulse response. Okay? And so you'll notice that this GUI is actually provided x, and then it's also flipped h for us and shifted it. And you can actually drag h back and forth here, and you'll notice there's a green dot at the bottom of the screen that tracks the total value of the integral of x times shifted h. So notice that because they don't overlap, they multiply together and get 0. But as I move it forward, and notice the green dot's moving as well, all of a sudden it starts to pick up a value. It picks up an area, and thus y of t picks up a value. And then that's going to continue on. And then from that point on, the area is actually going down as we move t forward because we're overlapping with the tail of the exponential, and so the value of y of t is actually going down. All right. The question is, how do we do that by hand?